brain has been feeling a little bit drained because of all the calculator stuff that we've been doing. Today is pretty basic. I mean, it really is. We're just going to cover some really basic stuff about probability. So this isn't going to be the toughest thing in the world that we've ever done. But we have to have some place to start, you know, so everybody needs to be at the same position as we work through this chapter. And in fact, this chapter is mostly just basic problem stats. So like I said, juniors, if we're going through this and you're thinking, oh no, I remember this, that's a good thing, you know. We've got permutations and combinations. And those are the names of ways that we figure out how many ways there are to do something. How many ways to count things that happen. So counting permutations and combinations is our objective. And we're not going to cover this one in one day. We're going to take this section over 2 days. So this says, the getting ready is pretty basic. It says, for lunch, in how many different ways could you choose? And we see a cafeteria menu here. You're going to have a sandwich, you're going to have a side dish, and you're going to have a dessert. So I always think of this in terms of slots. You know, you grab a lunch tray and you go up there, and it's a lot like the lunch that you guys have, the one that is the government-sponsored one. If you don't take all the stuff, then you get charged a la carte instead of getting charged the meal price. So we need a sandwich, we need a side dish, and we need a dessert. Well, to know how many ways that's going to happen, we need to know how many choices do we have for each one of those. So we go to the menu, and we see there are 4 different sandwiches. Got 4 choices. 4 choices for sandwiches. Got to pick a side? There's 3 of them up here. 3 sides to choose from. Have to pick a dessert. 1, 2, 3, 4. 4 choices. And in probability, whenever you want this and this and this to all happen at the same time, you multiply those together. 4 times 3 is 12. 12 times 4 is 48. So there would be 48 different choices. When Subway, you guys have had Subway your whole life, but when Subway first became a franchise, and Subways were opening all over the country, the first commercial that they ran talked about how many different ways there were to make a sandwich. And they gave this number, you know, in the millions. And of course, you know, all us math geeks sat there and figured out were they right with the numbers. Because they have to meet truth in advertising. And so they found out they had actually shorted themselves. They didn't think about the fact that when people come in, they say, you know, do you want bread? And at that time, you had to have bread. It wouldn't be Subway without bread. So you had to choose a bread. And then you choose a cheese. And what they didn't account for was that people might say, no, thank you. I don't want any cheese. So they had actually more choices than they had put in their commercial because they didn't count on people saying, I don't want that, you know. So that was one of the big math things when Subway came out. So 48 ways. Essential understanding is we can use multiplication to quickly count the number of ways that certain things can happen. When they're really basic, like the one that we just saw, we can do that. So our key concept is the fundamental counting principle. And it's fundamental just to know that when you have to have separate events that all need to take place at the same time, so you want this and this and this to happen, you multiply. That's what you do. Think of them separately and you multiply. So if event M can occur in M ways and it's followed by an event N that may occur in N ways, the event M followed by the event N can occur in M times N ways. Boy, oh boy, are they making that sound difficult. You look in the drawer, there's 3 pairs of pants and there's 2 shirts. How many choices do you have for outfits? Well, 3 times 2 is 6. That's it. That's the fundamental counting principle. You know, there's your choices. So that brings us to the problems they love to put on the MCAs, and they love license plate problems. absolutely love those, which is kind of good for us because they're not the toughest things in the world. The photos show Maryland license plates in 2004 and 1912. 2004, 1912. How many more 2004 style license plates were possible than 1912 style plates? So here's what happens. They make the first vehicles. They're not sure whether or not people are going to be able to afford automobiles. So they don't make a lot of license plates. They don't think ahead about the number of people that would eventually have vehicles. This would in no way cover the amount of people that are in Maryland now. They wouldn't have enough numbers for everybody because everybody has an automobile. They had to change it up. So it asks how many are going to be possible and really how many more. You know, what's the difference between these two? So I look at the first plate and I think, how many slots have to be filled with something on this plate? 3 letters and 3 digits. That's how you fill that license plate with the information that you need. And then I think, how many letters are there? A through Z, we have 26. So you could choose any of the 26 for the first slot, any for the second slot, any for the third slot. And then we get to the back 3, and those are digits. So you have to think, okay, how many numbers could I put in this slot for digits? 0 is an option. So I'd have 0 through 9, and that's actually going to be 10 digits. Now, they did eventually figure out there are certain license plates that you do not want to have out there for people. And so there were some that were offensive when there was repetition, and they decided, let's take that stuff off. And they don't allow those. But in the beginning, they said, let's just let this be whatever it's going to be. So to punch this in on the calculator and get the amount, I wouldn't punch it in as it is up there. We all know this is 26 to the third and this is 10 to the third. So we could just punch it in as 26 to the third times 10 to the third. I don't think people would like a plate that says 666. There was a movie that really made that into a bad thing. So 26 to the third times 10 to the third. That's a lot of license plates. 17,576,000 license plates. Didn't have that many available back in 1912. You know, this one is just 4 digits. That's all you have to choose from. And the digits are the same digits we used over here. It's 0 through 9. So, well, that's 10 to the 4th. It's 10,000. So way back in 1912, 10,000 probably covered the amount of people that could afford to buy a vehicle. But now we've got this little monster. So they want to know what's the difference between the two, which would mean we're going to take our 17,576,000 and we're going to subtract 10,000 from that. So that means we're just going to subtract a 1 from this 10,000 slot. There's our answer. So 17,566,000 license plates. That would be it. All right, down here. It says in 1966, they made a style change. They said one type of Maryland license plates had 2 letters followed by 4 digits. So now, got the 2 letters in the front, 4 digits in the back. And given the one we just did, I'm guessing you can do this one on your own. So go ahead and take a peek at that one. See what you get. much trouble with this. We've got the 26 letters. And then our 10 digits. And that gives us 6,760,000 different license plates. Now, if you're thinking that's a lot of license plates, are there even that many people that they would need that many license plates? I want you to think for just a second in your family how many running automobiles there are. And if you have 5 or more running vehicles in your home, raise your hand. How about 6 or more? Raise your hand. Got a few people there. So how many running vehicles? 7, 8. And there have been times I had one student that said they had 9. Their dad worked on people's automobiles, and so at any given time he would buy vehicles, and he was basically flipping them, like you would flip a house. He'd buy vehicles, he would fix them up, and then he would sell them. So, we like our vehicles in America, we do, so you're going to need a lot of license plates to cover all those people. Down here, a blank is an arrangement of items in a particular blank. This is where we get the important distinction between our objective of what's a permutation and what's a combination. Permutations are used for arrangements. An arrangement means that order is important. I'm going to give you an example. If you're running in a race and there are going to be ribbons for first, second, and third place, obviously you would prefer to have first place over second place, and second place over third place. So order would be important to you. But if I say, I'm going to just pick any 3 people out of here for a committee, and they're all going to be on the same level, they're all just committee members, it doesn't matter which order I tell people the names, they're all the same 3 people that are going to be on committee, so order doesn't matter. So when we think about something where, you care whether or not the order is important, that's where we're putting things in a particular order. That's when we use a permutation. So permutations are for ordered items. Example, suppose we want to find the number of ways to order 3 items. Right there, there's the word order. We could use the fundamental counting principle to get 3 times 2 times 1. And that's because we could go after this with the slot method, which is basically the fundamental counting principle. And say, okay, first slot, how many choices do I have to pick an item? 3. Those 3 items were sitting right here in front of me. I picked one, put it up there. Well, now I can't pick that one again. It's already been picked. It's the first one. So I go back over to where my items are. Now I only have 2 choices. And now I've put that item in the order on the shelf, wherever it was going to go. And I come back over, there's only 1 choice. That's all I have. So a permutation is basically just a way to use the fundamental counting principle and make things go a little faster. Here's why. When you're ordering all of the items, what you're really doing is creating a situation called factorial. Factorial happens when we have to take like 5 times 4 times 3 times 2 times 1. When you want to multiply a number and all of the consecutive integers below it down to 1, that's factorial. And factorial, we use the symbol exclamation point for. So permutations use that concept of factorial. And if you want to arrange them all, that's the fastest way to figure it out. So using factorial notation, we can write that 3 times 2 times 1 as 3 factorial. And the good news is, your calculator actually has that button on there. It's just something we haven't used a lot before because we haven't been doing probability stuff. So we turn her on and we go into math And you'll notice up at the top, it says we've got this stuff about numbers, and then we have this CPX stuff, which right now isn't going to make any sense to you, and it probably won't until calculus. But if we go to PRB, that's probability. And look at number 4. There's our exclamation point. So it'd be kind of silly to grab a calculator for 3 factorial, but this is how we would do it. We would punch in a 3, and then we'd go into math, and I would just use the left arrow instead of hitting the right arrow 3 times, and hit number 4, and enter. And there it is. So like I said, kind of useless for 3 factorial, but if we have to do 8 factorial, I'd rather punch in 8 factorial than 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it comes in handy to do that factorial notation. So n factorial, it looks bad again. We've got this n times n minus 1 times n minus 2. Just remember it's consecutive integers down to 1. That's what we're doing for factorial. So this says finding the number of permutations of n items. Got 12 folders sitting in front of you. In how many ways can you file 12 folders one after another in a drawer? You certainly could do this with slots, but you'd get going and you'd realize, wait a minute, I'm going to do that all the way down to 1. That's going to be factorial. So we just punched in this 12 factorial instead. 12, math, left arrow, number 4, 12. $479,001,600 different ways to order 12 files. So notice it said one after another. That's an ordering. They're telling us put one right after another. This one is, in how many ways can you arrange 8 shirts on hangers in a closet? So right here when I see arrange, I know I'm talking about permutations. And I can think of it in terms of slots if I want to, but I need to arrange all 8 of those. So go ahead and find that answer. Start over here this time. Well, that didn't take long. I guess you guys are already punching that in while I was still yakking about the other stuff. So 8 factorial was 40,320 different ways. What we have to be careful about is right now, we're not having to choose between permutations and combinations. Most of the stuff we've talked about so far, well, in fact, all of it has just been permutations. But watch out for words like arrange and order or something where they're saying specifically place things this way. And what should we do if we want to look at just a few permutations instead of all of them? For instance, take those 12 folders, but you don't have time to arrange them all. Right now, you just want to pick the 4 most important ones in order of importance. You don't want to do them all. So then what we're doing is just say, okay, I can only get these 4 done. Okay, this is the most important one, put it up on the shelf or put it in the file cabinet. This is the next important one. You get the 4th one done, you know you got a meeting to go to and you have to leave. So how many ways would there be to do that? Now again, this is only 4 numbers. It wouldn't take us very long to multiply that out. But there's a better way, and that better way is to use permutations. So in this example, it's saying the number of permutations of n items of a set arranged r items at a time, and I know that's really confusing, but in the last one that I was just talking about, this would be, I had my 12 files, and I wanted to pick 4 of those and arrange them. So this is the total that I have to choose from, and this is the how many I want to do right now. It's written this way. N, and it's a lowercase n, this is actually a subscript, and then an uppercase P, and then a lowercase r. And that means this is a permutation of n objects chosen r at a time. So NPR. Now that gives us a little formula here, and that formula is going to be n factorial over the quantity n minus r factorial. Seems a little weird, but let's see why this works. In the example I just did, 12 factorial is the total number of files that I have to choose from. I didn't want to do them all. I don't want to order them all. What I wanted to do was I wanted to order just the first 4. So down here, I would have 12 minus 4 factorial. Okay, so this would really be 12 factorial over 8 factorial, which makes sense if you see it in expanded form, because this would be 12 times 11 times 10 times 9 times 8 dot 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 over 8 times 7 times 6 times 5 dot dot dot. And you realize if this is all multiplication, I could cancel anything on the bottom with anything on the top that's going to be exactly the same. And that means anything from 8 on down is going to cancel out. And that gives me exactly what the fundamental counting slot principle would give me by doing that. So that's why this formula works the way that it does. So in this case, they had 10 total objects, but they only wanted to arrange the first 4. So it was 10 factorial over 10 minus 4 factorial, which means it was 10 factorial over 6 factorial, and I can't help it, in my head I'm already doing this. Because anything after 6 is going to cancel out. So, actually, might be able to do that one in your noggin without having to use a calculator for 5040. So that's how permutations work. And, I don't know if you noticed this before, but that's also on our graphing calculator. So underneath math, probability, look at number 2. There's permutations right there. So if we wanted to just turn it over to the calculator and turn our brain off, what we would do is say, okay, if I want 10 P4, I'm going to punch in 10 math, probability, number 2, and then I'm going to punch in a 4. And that tells the calculator that the n is 10 and the r is 4. Gives me the 5040. If you're going to go further in probability and statistics, it's best to think your way through it in terms of what are those slots, what would be working here, and how would this cancel out. Because factorial is used a lot in prob and statistics, so we need to know how that works. So next page says we've got some track going on here. And we have 10 students in a race. First, second, and third places win medals. Ooh, places. That means an arrangement. That means order matters. That means I'm talking about a permutation. And it says, in how many ways can 10 runners finish? First, second, and third. So what we're doing is we're using a permutation. There's 10 total runners, but we only care about first, second, and third place. That's picking 3 of them. So this would be 10 factorial over 10 minus 3 factorial, which is 10 factorial over 7 factorial. And I think through that and I realize, well, that's just going to be 10 times 9 times 8. Because the 7 on down is going to cancel out with the bottom here. 720. And there it is. Or you grab the graphing calculator and you punch that in. So by using permutations, it could become a totally calculator-driven thing. Or we go back to slots and say, there's only 3 slots here. 10 people could win first place. But now one of them won first place, so they're not eligible for second place, so now there's only 9 of them. And since those 2 people are already up there, now there's 8. So whether or not we use the permutations or we use the fundamental counting principle, we'll get the same answer. Doesn't make any difference. And there's a wonderful little got it down here, and it's been way too long. It's been a long week with a lot of showing you stuff on the graphing calculator, so I haven't had you doing candy partners. I thought we were going to do candy partners, so go ahead and get started on Got It 3A. You could go ahead and do B too. I'm sure you guys are already getting this. How many people are going? Already, candy up there. Find that candy partner. Talk to them about what you're doing, what they're doing. Remember, if you can't find your partner, come forward. I'm sure we can figure them out pretty quick. Quiet. Either everybody had exactly the same answers as a partner, so they didn't need a discussion, or your partner wasn't quite done. How many ways can 15 runners finish first, second, third, everybody? What'd you get? 2,730. So, okay, I'm interested in this. How many people use the fundamental counting principle on the slide? Okay. So, the rest of you all use permutations. How many of you use the calculator? Okay, and that's because some people, whole calculator and trusting and putting this all in the calculator's lap doesn't come very easily. And both of them will give you the same answer. Doesn't matter which one you use, and you get the same thing. Now, I did see a couple of varied answers for B. It says in problem 3, is the number of ways that the runners could finish first, second, and third, is that the same as the number of ways that they could finish 8th, 9th, and 10th? What do you think? So as I was walking around, I saw quite a few people had yes, but there were some people that had no. So the question is, does it matter that you're ordering them in first, second, and third place versus ordering them in 8th, 9th, and 10th place if you know absolutely nothing about the runners to start with? It doesn't make any difference if we know absolutely nothing about the runners to start with. And that's because we're still just counting. That's all we're doing. We're just counting. So for B, it said, is it the same? Yeah, it is the same. And that's because the total number of runners that we were sticking with was 10. And the number that we are picking is 3. It doesn't matter where they are in the order, they just have to be in the order somewhere. So NPR, it would be exactly the same amount of permutations. Now, if all of a sudden we start to know something about the competitors, like we have records of their fastest times and things like that, well, then it doesn't become so much a counting principle as it is probability. And right now we're just talking counting principles. How many would there be? Alrighty. 4, 3, 2, 1, 0 me. This is our first day on prob and stat stuff. Where do you think you're at? Like I said, most of the time I'm wandering around, everybody's got the answers before I even came down there. So thank your partner. Head on back, and we'll give you a little bit of practice here on some probability counting principles.
Yeah.